Let us move on to another wave transformation phenomena known as wave diffraction. Actually, wave diffraction process is very similar to sound diffraction. As we can see on the figure here, diffraction typically occurs when the wave actually propagates through a gap, so that the wave energy that is able to reach the other side spreads out in semicircular patterns. We refer to the incoming side as the C side, whereas the outgoing side as the Lee side. So diffraction occurs when wave is truncated as it passes an obstacle, such that the wave height of the wave crest varies along the ring or the fan and thus induce flow of energy laterally along the direction of reducing wave height. What does that mean? So if you look at this wave here, this wave front, when it approaches this gap, the wave front here, which hits the obstacle, they are going to be reflected. Okay, we'll talk about reflection later on. So they are going to be reflected back to the C side. Only the wavefront that reaches this gap is able to pass through to the Lee side. But when this wavefront passes through to the Lee side, the wave only exists from here to here. There's no wave on the Lee side of this obstacle. There's no wave on the Lee side of this obstacle. So there's a truncation. That means the wave is suddenly being cut off on this end and also on this end. Of course, the wave cannot continue to propagate forward only with that short section, because there's a discontinuity in its lateral direction. So what it's going to do is that it's going to spread out its energy to both sides here, and as a result it makes a ring shape or a fan shape like this. And of course, since the energy is spread out to this side and this side, so the overall wave height typically will reduce, because the energy will have to fill up or be shared with these two sections. So as the diffraction propagates, continue onwards, then the wave height will continue to reduce. This slide here shows a very interesting wave diffraction phenomena. What we can see here is a headland, and there's actually an island here which is very close and forms a part of the headland, whereas here we have an offshore island. Now the predominant wave direction is coming from here in this angle, all right? And so as it approaches this gap, you will notice that there is this diffraction effect that has taken place. And of course, we also take note that the part of the wave here eventually also becomes refracted and becomes almost normal. The orthogonal becomes almost normal to the shoreline. But meanwhile, so the same wave that is coming in this direction is also truncated at this tip of the island, and you notice there is also a diffraction effect from this side. And that actually means that on the lee side of this island, this wave is coming from this direction, so we call this the C side, and this is the lee side. So you notice on the lee side of this island, it actually has diffraction effect from this gap, and it also have diffraction effect from this side. And these two diffraction or diffracted waves actually superimpose with one another on the lee side of this island. We will learn how to solve this problem later on. So basically, the wave diffraction phenomena is described by this Hart-Jens principle. We already mentioned just now that when the incoming wave is suddenly truncated on both sides of the gap, then its wave energy will be spread out, right, causing the wave height generally to reduce. Here we are looking at an animation of wave diffraction. On the left, we have the wave diffraction from a single gap, whereas on the right, we see wave diffraction from multiple gaps which are very close to one another. As you can see, when the wave is diffracted through a single gap, it forms this semicircle, the fan shape. But when it is diffracted through more than one gap, then each of the gap produce its own diffraction pattern, and eventually all the diffracted wave on the lee side will superimpose with one another and produce a much more complicated wave pattern. With this, we want to introduce the diffraction coefficient, KD. All right, and since diffraction typically happens due to an obstruction, right? So we want to refer to the obstruction generally as a barrier. The obstruction may be an island. It also may be a man-made structure such as wave breaker. We will learn more about wave breaker eventually. So let's say if this barrier has a tip at this point, and assuming that this is the incoming wave crest, so that the wavelength is L, and this is the orthogonal or wave incidence direction. Now, because of the wave incidence towards this barrier, this part of the wavefront will hit the barrier and reflected back to the sea side, but that is not our discussion right now. Our discussion will focus on this part of the wavefront, which is suddenly truncated on the lee side, and so it fan out and form this semicircular shape on the lee side of the barrier. And we will try to find out what is the wave height at a point of interest on the lee side. So if we have an incidence wave height of Hi, we want to find out what is the diffracted wave height Hd at a particular point of interest. This point will be defined as located at a distance of r away from the tip. This point is oriented at an angle beta from the barrier, and the incidence wave angle is oriented at an angle theta from the barrier. So the diffraction coefficient is then defined as the diffracted wave height over the incidence wave height, and we can be quite certain that the diffraction coefficient is always less than 1, which means that the diffracted wave height is definitely always smaller than the incidence wave height. This table here shows the typical diffraction coefficient KD value for a semi-infinite breakwater. So basically for a barrier like what we see earlier on the definition figure, which is semi-infinite, that means it ends, it has a tip at a certain point. So the KD value depends on beta. The table gives us the value from 0 to 180 degree. Beta is the angle of the point of interest on the lee side. So it may range from 0 to 180 degree. Of course, the table only shows us a specific angle. In the event that we might want to solve for location at any other angle, we will have to do interpolation. And of course, the KD value also depends on the incidence wave angle, theta. The table also shows limited range of theta value. We have 15 degree, 30 degree, 45 degree, and so on. And again, if we need to solve anything other than is shown on the table, then we may have to use interpolation. Last but not least, the KD value further depends on the ratio of R over L. R is the distance of the point of interest from the tip of the barrier. L is the wavelength of the incoming wave. So instead of solving the KD in terms of the actual R value, as usual, we actually use the normalized term. So we relate R with the wavelength. So we have R over L ratio here. So these are the different R over L ratio. You notice that it again is given in a specific range only, from R over L of 1 over 2 to R over L of 10. This slide here is a continuation of the previous table. And likewise for this slide, so we have the theta value up to 180 degree. The table just now allows us to solve or find out what is the KD value for any incidence angle theta. This chart here, meanwhile, also allows us to determine the KD value graphically, but it's limited only to normal incidence, which means that theta equals to 90 degree. If we look at this chart, the barrier is located here, so that we have Y over L, which is the direction laterally along the wavefront, and wavefront is approaching this barrier at a normal incidence. And on the lee side, we have X over L. X is the direction of the wave propagation. So as we can see, we expect that the wave that goes to the lee side of the barrier will be diffracted with this circular patterns. If we want to solve for a particular location on the lee side of this barrier, then we will have to find out what is the value of Y over L and X over L of that location. XY is the coordinate to describe that location with the origin at the tip of the barrier. So if we know XY value of the location, then we can find X over L and Y over L value of the location, so that we are then able to read the KD value, which is on the dashed line here from this chart. We notice that KD value equals to 1 in this dashed line, meaning that the wave on the left hand side of this dashed line is not diffracted. The wave front on the left hand side of this line is able to retain their original wave height, meaning that when the wave propagates into the lee side of this barrier, only the wave front in this part only the wavefront in this part that will spread out its energy to form the semicircular pattern here. The wavefront on this part is too far to spread its energy all the way to this part. So this section here is unaffected. So if KD is equals to 1 here, we notice that somewhere along here KD has dropped to 0.6, 0.5, 0.4, 0.3, 0.2, and 0.1. Right now, let's look at an example. Consider a 5-meter wave, which means a wave with a wavelength of 5 meters, approaching a barrier at an angle theta equals to 90 degrees. Determine the diffraction coefficient at a location which is situated at a distance r equals to 25 meters away from the tip of the barrier, which is here, this point. And so this point is located at an angle beta equals to 90 degrees. Alright, so if theta is 90 degrees and beta is 90 degrees, if you check the table, they are available from the table. And if r is 25 meters, whereas wavelength L is 5 meters, so r over L is equals to 5. So if you go to the table just now for theta equals 90, beta equals 90, and r over L equals to 5, you should be able to find that the wave diffraction Kd equals to 0.5. Alternatively, we can also use the chart, because x here is the distance of the propagation, x is equals to 25 meters. Y is the direction along the wavefront, direction of the wavefront. So at this position, y is equals to 0. So if x over L is 25 over 5, y over L is 0, then you can also use the graphical method to find the Kd value, which is approximately equals to 0.5. For theta equals to 90 degrees, which is this group here, and for beta equals to 90 degrees, so that leaves us with this column here, and for r over L equals to 5, the answer is 0.53. For y over L equals to 0, we are looking at the position over here. For x over L equals to 5, we are looking at this line here. So this line, and right here at y equals to 0 is approximately on the dash line 0.5. The solution that we get from the table and the graphical method should be close, but there is no it's not going to be always the same. So we may conclude from this analysis that the wave height at this particular location is about 0.5 or half of the incidence wave height. Right now, please try this example on your own, and we will discuss the solution online. Right now, let us look at another example. Here we have a figure, but to avoid confusion, please let us focus first on the figure on the right, which is the actual problem. Now consider a 6-meter wave approaching a barrier as shown in the figure, which is this one. Determine the diffraction coefficient at location A, which is at this point. So we have a semi-infinite barrier which ends at this point. The incoming wave is approaching at an angle as shown here, and we want to find out what is the diffracted wave height at this point A, which is 30 meters away from this tip here and 30 meters away in this direction as well. Now, if we look at this problem, you will realize that the barrier is actually located in a different orientation or different direction compared to our definition sketch that we used earlier. Because in our definition sketch, the barrier is on the left-hand side. So how does that affect our solution? Now, we are interested to solve this problem. if we mirror the image of this problem, then we get this. And you notice that this wave is actually approaching the barrier at 120 degrees. So if we just look at the problem sketch, we need to be careful that by definition we need to use this angle. Theta should be this angle. Theta is defined as the direction of the incidence wave measured from the wave barrier in this direction. And likewise, in terms of A, the x is measured in this direction, so in either figure it will be the same. The y would measure in the lateral direction, it is the same. So we want to be careful of the definition of the angle theta and also the angle beta when our actual problem is not oriented in the same pattern as our definition sketch. So if we have clarified that, which means that right now in our problem, theta is 120 degrees, beta is 135 degrees, because beta is also measured from the wave barrier here all the way to this line, this direction where A is oriented from this tip. So beta should be 135 degrees and not 45 degrees. R is the distance of A from the tip, so that is straightforward. It's 42.4 meter. So ROL is obtained for the 6 meter wave is calculated as 7.067. So right now, since this incoming wave is at an oblique angle, which means an angle other than normal incidence, so we are going to use the table. We are going for theta 120 degree, beta of 135, ROL, what we have from the table is 5 and 10 only, but what we require is for 7. So we will do some interpolation here to obtain the diffraction coefficient, which is approximately 1.06. Here we have another example. In this case, we have a wave that is approaching a gap, which means that we have two barriers here, barrier 1 and barrier 2. So we consider a 6 meter wave approaching a gap between two barriers as shown in the figure. Determine the wave height at a location A, which is shown here, for a given 2 meter high incident wave. So how do we solve this problem? What we need to do is that we are going to find the diffraction coefficient due to barrier 1. The incoming wave is oriented at 120 degrees away from barrier 1. Point A is oriented at 135 degrees away from barrier 1. So the diffraction coefficient, as we have just solved in the previous problem, is 1.06 due to barrier 1. But if we look at barrier 2, the diffraction coefficient for barrier 2 will be solved based on the incidence wave angle. The incident wave angle is actually 60 degrees from barrier 2. And A is located at 90 degrees from barrier 2. So you should be able to check from the table that we get the diffraction coefficient as approximately 1.04. So which means that for the incidence wave height, it will be increased by the factor 1.06 due to barrier 1, and it will be increased by a factor of 1.04 due to barrier 2, so that the final diffracted wave height is the two diffraction coefficient multiplied to the original incidence wave height of 2 meter, and we get a final solution of 2.2 meter.